How many universes are there? Some scientists argue that space is too vast to contain only our universe. However, for a long time, researchers have not been able to prove other universes existed, but that is no longer the case as a new study has turned up evidence of a parallel universe that not only exists but has time running backwards. What is this newly discovered universe like, and why does time not run as it does in our universe? Stay tuned as we bring you the latest NASA discovery of a parallel universe that runs backward through time. The multiverse is a term used by scientists to describe the idea that other universes may exist in addition to the observable universe. Several scientific theories predict multiverses, which describe various possible scenarios ranging from regions of space in different planes than our universe to separate bubble universes that are constantly springing into existence. In 1848, Edgar Allan Poe published a prose poem in which he imagined the existence of an infinite number of universes. However, the fact is that these parallel universes are no longer limited to science fiction. Philosophy, physics, and even theology have theories about why and how multiverses exist. Parallel universes have frequently been used as an explanation for strange phenomena in fiction and television shows. Scientists have proposed 4 different types of parallel universes. A Type 1 parallel universe assumes that space is infinite, which it very well could be, and that the physical laws of these other universes are the same as ours, but that they are so far away from us that we are causally disconnected, which means that no messages can be received or sent because we can only receive messages from within our own Hubble volume. A Type 2 parallel universe is entirely dependent on 2 theories which incidentally may possibly prove this type of multiverse: the inflation model and the ekpyrotic theory. Because of ongoing inflationary processes in these and our universes, space between the other universes and ours is expanding faster than the speed of light, making communication impossible. A Type 3 parallel universe is the alternate or mirrored reality universe, which is what we all usually think of first. This type of parallel universe emerges from quantum mechanics' many worlds interpretation (MWI) to approach the phenomenon of wave function collapse. According to the MWI, for every possible quantum option, there exists another universe in which that option is realized. For example, if you come to a point in your day where you are torn between 2 drinks, say a glass of water or a bottle of Dr. Pepper, a Type 3 parallel universe says that in the alternate reality, you actually choose to enjoy a glass of the good H2O instead of the Dr. Pepper you did choose. A Type 4 parallel universe implies that the mathematical equations and physical laws that govern these universes differ greatly from our own. The MWI parallel universe is based on the idea that these coexisting universes correspond in some way, whereas Type 4 parallel universes can follow laws that are completely contradictory to ours, with both being equally valid. The idea of the multiverse has given rise to several theories, and one of them is the expanding cosmological multiverse. This is a theory that can be directly traced back to cosmology, specifically the discovery that our own universe is expanding. This multiverse concept asks if the initial rapid inflation that our universe experienced 13.8 billion years ago could be happening in distant regions of space-time disconnected from our universe. The fundamental idea is that our universe is a distinct patch of space-time that is evolving as a distinct entity. This region is homogeneous, isotropic, the same in all directions, and rapidly expanding. If you trace the evolution backward in time, you will discover that the universe is about 13.8 billion years old. It is also believed that other regions of the multiverse may be experiencing their own Big Bangs and, as a result, expansions. This means they have no power over our universe. They are thus other universes, and the multiverse is the collection of all such universes. It gained popularity in cosmology because it could address long-standing mysteries while remaining consistent with existing physics. One reason the concept of the multiverse became popular is that it can naturally arise from the theory of inflation. Although inflation in our universe ended 13.8 billion years ago, quantum effects can always bring inflation back in another region of space-time. This results in bouts of inflation never ending, referred to as eternal inflation, and the possibility of an infinite number of different universes. Andrei Linda, a Russian-American theoretical physicist, proposes one arrangement for this multiverse. He imagines universes as bubbles expanding on a cosmic canvas, squeezing away from one another in bouts of eternal and chaotic inflation. The question of how these universes within a multiverse would differ is currently being debated, but some think there is no reason to believe that the laws of physics would be the same in these distinct regions. And so one reason these other universes are interesting is that they may have different versions of physics laws. This variation could apply to a variety of physical parameters, such as gravity and the rate at which the universe expands. This means that some of these universes may have physics laws that are unsuitable for the formation of large-scale structures like galaxies or stars. They could even have different fundamental particles. As a result, these universes are not variations of our universe and thus cannot support any life, let alone a version of you or me. Another multiverse theory is the string theory. String theory is a physicist's proposal to connect quantum mechanics and general relativity, which are the best descriptions we have of the infinitesimally small and incomprehensibly large. String theory is based on the idea that fundamental particles such as quarks and electrons are actually a single point in one-dimensional strings vibrating at different frequencies. And because of one of the key elements on which string theory is based, this string landscape provides a popular setting for the multiverse. String theory requires extra dimensions to exist in order to be mathematically sound. But these aren't the parallel dimensions seen in science fiction. String theorists believe that these additional dimensions are curled up within the three traditional dimensions of space, and yet they are still invisible to us because we evolved to see only in 3 dimensions. These extra dimensions may provide a doorway into the string theory multiverse. But even if this were the case and there was a connection to other universes via these dimensions of space, they may remain permanently out of reach and view due to the fact that the universe's inflation means that there is a cosmic horizon beyond which we cannot see. If there is no connectivity between universes in a multiverse, it is nearly impossible to test the cosmological concept of a multiverse experimentally. There is also the black hole multiverse theory. When a massive star runs out of nuclear fusion fuel, it will collapse into a black hole, a region of space-time bounded by a surface called an event horizon from which nothing, not even light, can escape. According to Einstein's general theory of relativity, a large mass can bend space-time. According to the theory, the heart of a black hole has a singularity where the mass is so great that the space-time curvature becomes infinite, and as a result, the laws of physics fail. This is a difficult concept for physicists to grasp, but one hypothesis suggests that the singularity could be replaced by an entire universe and thus a multiverse. Singularities are non-physical in the sense that they cannot be measured. That is, their existence indicates that a theory is lacking. In this scenario, every black hole creates a new baby universe inside, on the other side of the event horizon, and this baby universe becomes an Einstein-Rosen bridge, also known as a wormhole, connecting this infant universe to the parent universe in which the black hole exists. According to this theory, the parent universe appears as the other side of a white hole, a region of space that cannot be entered from the outside and can be thought of as the inverse of a black hole. Blowing a soap bubble through a circular wand could be an analogy for matter going to a black hole and ending up in a new universe. The wand represents the event horizon, albeit in one dimension less. The soap liquid represents matter crossing the event horizon, and the bubble's surface represents the new universe. According to this hypothesis, a universe can produce billions of black holes, each of which can produce a baby universe. Researchers at the International School of Advanced Studies in Italy estimated in January of this year that there could be as many as 40 trillion, that's a 4 followed by 13 zeros, black holes in our universe alone. That is a lot of miniature universes. These infant universes would be hidden from the occupants of their parent universe by the event horizon's light-trapping surface, and once that event horizon is crossed, there is no turning back. That, combined with the fact that nothing can enter a white hole, which is still purely theoretical but permitted by general relativity, means that there can be no interaction between parent and infant. However, if two black holes existed in the same universe and each of these black holes created a new universe, then there is a possibility that these two sibling universes could merge, just as two black holes merged to create one black hole. In a baby universe, this would manifest as a large-scale asymmetry in space. This means that if we ever discover a preferred direction in our universe, say one with increasing matter and energy, we could attribute it to our universe interacting with a sibling. So fascinating is the many worlds multiverse of quantum mechanics. The term multiverse does not exist in quantum physics, which deals with subatomic physical laws. Alternate universes are referred to as many worlds and are part of a radically different concept, as they are not geographical in nature like the previously explored multiverses. Hugh Everett III, a physicist from the United States, proposed the many worlds hypothesis to explain how a quantum system can exist in seemingly contradictory states at the same time, a phenomenon known as superposition, and how these paradoxical states appear to vanish. Consider Erwin Schrödinger's infamous thought experiment, Schrödinger's cat, to visualize the effect of many worlds on the existence of a superposition of states. A helpless cat is placed in a sealed box with a device containing a vial of lethal poison, which is released only if an atomic nucleus in the box decays. Each state, in this case dead or alive, is described by a wave when the box, the cat, and the device are treated as a single quantum system. Because waves can overlap to form a single wave function, the cat can exist in a state of superposition. This means that the cat is both dead and alive in quantum mechanics. This seemingly contradictory state lasts only until the box is opened, analogous to performing a measurement on the system, and the wave function collapses, indicating that the superposition has vanished and the state has been resolved. Either the cat is dead or alive. However, why measurement causes this collapse of superposition, also known as decoherence, remains unknown. The many worlds hypothesis eliminates decoherence entirely. Instead of the opening of the box collapsing the wave function, it appears that measurement causes it to grow exponentially and swallow the experimenter and eventually the entire universe. Each state of a system is a physically distinct world in quantum mechanics' many worlds formulation. This means that each light switch flick would create an almost infinite number of worlds, one for each photon's possible path as light fills your living room, not just a world where you didn't flip the switch at all. Which means in Schrödinger's cat thought experiment, the experimenter is not opening the box to determine whether the cat is dead or alive. Rather, they are opening the box to discover whether they are in a world where the cat is dead or alive. At first glance, the worlds that comprise this quantum multiverse appear to be identical, with only the most minute differences. However, these changes spread from universe to universe, so those that diverged earlier may be noticeably different. According to this theory, observers' objects, events, and physical records will differ in different worlds. For example, there's a world in which the Eiffel Tower is located in Los Angeles. But every world or every universe is a part of a single global universe. And now NASA has joined the hunt for parallel universes with a special experiment that it's been conducting in one of the coldest parts of the world. The experiment is connected to two mysterious signals from Antarctica that have been baffling researchers. A high-energy particle appears to have burst straight up out of the ice twice now, tripping detectors on a balloon-borne experiment floating overhead. It's as if the particles escaped the entire Earth unscathed. However, that should be nearly impossible. None of the known particles, which collectively are described in a physics model known as the Standard Model, can make that trip at high energy levels. Particles that are otherwise identical can carry varying amounts of energy, and the amount of energy carried by a particle can change its behavior. Low-energy neutrinos can pass undetected through the planet's crust, molten rock, and iron. However, they lack the power to generate the signals found in Antarctica. The signals can be produced by high-energy neutrinos. However, because these higher energy neutrinos have larger cross-sections, they impact a larger region of surrounding space. They tend to collide with objects rather than pass through them. It is the equivalent of throwing a marble through a fishing net and attempting to shoot a beach ball through the same gaps. There is no known high-energy neutrino capable of passing through the entire Earth and emerging from Antarctic ice. The two detections were caught by NASA's Antarctic Impulsive Transient Antenna and NITA project. The scientists compared NITA's findings to those of IceCube, a much larger neutrino observatory in Antarctica, and discovered more evidence that they had discovered something never seen before. NITA is a stratospheric balloon payload that is flying over Antarctica. Through radio wave signals, this balloon was designed to detect cosmic ray air showers. These signals were detected to be bouncing off the ice and were to be tracked as they descended or ascended after the ice shelf bounce. It consists of a network of radio antennas attached to a helium balloon flying at 37,000 meters above the Antarctic ice sheet. To get an idea of how high that is, know that commercial flights fly at nearly a fourth of that height. The height is important here because it allows the NITA antennas to listen to the cosmos and detect high-energy particles known as neutrinos, which constantly bombard the planet. Radio signals can contain a wealth of information about particles with extremely high energies. When NITA was created, it was intended to hunt for an unusual event predicted by the Standard Model. High-energy tau neutrinos, one of three neutrino flavors, the others being electron and muon neutrinos, are among the most enigmatic particles in the Standard Model. These neutrinos should be hitting Earth fairly frequently from deep space. They are, however, difficult to detect. When tau neutrinos collide with something and decay, they create another type of particle known as a tau. The hope was that tau neutrinos would hit Earth at shallow enough angles in Antarctica that they would decay in the ice, producing a tau particle and a distinctive, detectable radio signal from the tau's passage through the ice. The waveform of that radio signal is predictable: a big spike, a big dip, a smaller spike, and a smaller dip, a shape largely determined by the Earth's magnetic field. And it would strike NITA from below and to the side, demonstrating the glancing angle with which it collided with the planet. NITA has detected a number of such events, as well as signals from cosmic rays coming straight down from deep space. When this occurs, an energized particle, possibly a proton, enters the atmosphere over Antarctica, bursts into a shower of smaller charged particles, and emits a radio burst that reflects off the ice before hitting NITA. Again, these events generate the same wave shape as tau neutrinos. The shape is largely determined by the Earth's magnetic field and contains only faint hints of the particles themselves. But NITA can tell the difference between a tau neutrino and a regular cosmic ray. When radio waves strike the ice and bounce up at NITA, their shapes flip. NITA sees the reflected down-up of a cosmic ray rather than the up-down of a tau gliding through the ice. And as they bounce off the ice, cosmic ray signals can strike NITA from any direction. However, the two NITA anomalies did not fit into any of the categories. NITA detected the unmirrored waveform that would indicate a tau neutrino, up, down in each case. But the wave hit NITA at such an acute angle that it would have had to pass through an impossibly thick chunk of Earth to arrive without bouncing. It was an unexpected signal from NITA's designers, and it hinted at the possibility of new, unknown particles bursting up from Antarctica. The finding implies that these particles are actually traveling backward in time, suggesting evidence of a parallel universe. The only way the tau neutrino could behave that way, according to NITA principal investigator Peter Gorham, an experimental particle physicist at the University of Hawaii, is if it changed into a different type of particle before passing through the Earth and then back again. Gorham, the lead author of a Cornell University paper describing the strange phenomenon, stated that he and his colleagues had witnessed several of these impossible events. While not everyone accepts this, the simplest explanation for the phenomenon is that at the time of the Big Bang, 13.8 billion years ago, two universes were formed, ours and one that, from our perspective, is running backward in time. If there are inhabitants of a possible parallel universe, they would regard us as backward. Skeptics, however, have proposed different explanations for the findings of Anita, including one recently proposed that the signals in question came from above and were only reflected by the ice. This is a scenario that the researchers had already considered and ruled out, though. Reflection is typically detected by specific changes in the radio signal that it causes. Another research team, however, suggested that these changes do not occur when radio signals are reflected by layers of thinner ice beneath the surface, which is a common feature of Antarctica's landscape. If this is confirmed, the strange measurements will be revealed to be ordinary cosmic rays. Meanwhile, the scientists behind Anita are working on an improved version of the experiment, Pueo, a larger antenna-carrying balloon that will be more efficient in catching radio signals when it launches. While carrying out its mission of studying energetic neutrinos from space, its operation will provide more clues about the nature of the anomalies as well as possible previous experimental issues. Let's hear what you think of parallel worlds.